Hello everyone, I'm Dr. Andrew Halfpenny, I work for HBK and I'm the Director of Technology for the ENCODE product brand. I'd like to talk today about quantifying the effects of uncertainty in correlating fatigue life simulation with physical tests, or as we called it, simulation, verification and validation. So first of all, what's the motivation for this? I was talking to the chief engineer of an automotive OEM a few weeks ago, and he put it very well this way. He said, in the past, if we had reliability issues with an oil pump, for example, we'd swap it out early under warranty. But EV batteries contain thousands of unserviceable components. They've got a mandatory minimum 8-year or 100,000 mile warranty. And if there's a reliability issue here, it could sink the company. And I think that just illustrates the magnitude of the challenge. Of course, that challenge then filters down to the reliability and the durability engineer. The head of reliability put it this way: over a warranty period of 8 years or 100,000 miles, I require greater than 95% reliability. That means fewer than 5% failures, with no less than 90% confidence in my estimation. In other words, we have a period, we have an expected number of failures in that time, and we also have a confidence interval in order for him to sleep at nights. We know from our experience of statistics that that will require tests in order not just to predict an average life, but to look at the distributions of life. And we know that fatigue is a highly variable subject. Looking at that as a design description, it makes me think about the good old days when all we had to do was pass a sign-off test. Today, the challenge is much greater. And that's what I want to talk about in this presentation. So I want to split it into these 4 parts. So first of all, I want to introduce simulation, verification and validation. And in particular, I want to introduce, moving on from deterministic design, which is the way we've designed things historically, to a new process called stochastic design. And I also want to reflect on how this impacts fatigue, in going from the old fatigue methods of build it, test it, fix it for new innovations, to simulation, verification and validation. Once we've done that, we'll have a look at how simulation and test can work together. Then we'll have a look at how we quantify uncertainty, because in order for them to move together and for us to validate simulation through test, we have to understand uncertainty. So we'll talk about how do we do that? Where does the uncertainty come from? How do we model it mathematically? And we'll finish with a case study. And then at the end, we're going to end up with the conclusions. The historic way of doing fatigue design is what we call a deterministic design. Deterministic design is a one-shot analysis. We first of all take all the loads, all the stresses, and we factor them up. That now assumes the very worst cases all act simultaneously. Then we take the strengths and we factor them down to assume that we've got the worst case materials with the worst case production effects and so on. And finally, we add a safety factor to account for uncertainties or modelling errors. Of course, the variability in the inputs and the outputs, that's unknown. Our risk of failure is unknown, but hopefully if the factor of safety is so big, then we can sleep well at nights. I remember in my very first job, I was designing a bridge in a shopping centre, and the loads were huge. And I remember going to my supervisor and saying, where did these loads come from? They're massive. And he says, well, you have to think about the worst case scenario. Let's suppose that a circus comes to town and a herd of elephants are crossing your footbridge. And then suddenly a mouse runs underneath and they all stop dead and they all look over the same side. That's your worst case scenario. And I couldn't help but think, how are the herd of elephants going to get on my footbridge in a shopping centre? But that's the way it goes. Of course, now we want to introduce probabilistic or stochastic design. In stochastic design, stochastic means statistical. So here we're trying to now measure the variability and the uncertainty that we have in our loads, measure the variability and uncertainty in our strengths, and then we're going to simulate those models to find out what is our probability that our most severe user is going to get hold of our worst production model. So by doing this, we can simulate the models with the tests, and we can validate the tests with clear and quantifiable risk of failure. That's what we're after. So in the beginning, when we go back to fatigue, we used to do it before simulation came in. We'd just use test. And we'd first of all generate a concept, we'd build a prototype, we'd test it, and if it was okay, we'd go into production. Of course, if it wasn't okay, we'd have to fix it. And this was a really expensive and time-consuming process of actually going, fixing the problem, and then coming back and building a new prototype to retest. And very often, we would run out of time and we'd have to go into production anyway. Part of the reason in that is by fixing one problem, we often create another problem which could be completely different. By addressing durability, for instance, we may hit a cost problem, or we may hit reliability or styling issues, for example. The other problem is, can we test every conceivable failure mode? That's a lot of tests. And if it's a novel component, do we even know what every conceivable failure mode is? So around about 2 decades ago, or maybe slightly longer, we started to bring simulation into this. And we introduced the 5-box trick when it comes to fatigue. In order to predict life, we do a fatigue analysis. And that fatigue analysis takes 3 inputs: the loads, the geometry, and the materials. The loads are the loads that are coming in. They're the loads in kilonewtons. The geometry changes those loads from kilonewtons into stresses in megapascals or strain. And then the material properties change those stresses and strains into fatigue life. Of course, with our battery, those loads can come from several sources. There may be structural chassis loads, but they could also be inertial loads as the battery mass is being shaken around over rough road surfaces. And of course, there are thermal loads too, due to constrained thermal expansion as the battery heats up and cools down. Now, the nice thing is, in simulation, we can model those in CAD and FEA. We can run through them and we can iterate that in order to get the design that we're after. Now, no one actually ever trusts a simulation, so you're still going to have to sign it off. So the sign-off test comes. We build a prototype, we subject it to qualification tests, and then we can measure the life. Now, to do that, we need to make sure that the test and the simulation share the same loads and the same boundary constraints. Now, I know that sounds really obvious, but really, up until about a decade ago, it was very normal to do simulation of real loads and then an accelerated test. So it was never possible to correlate the two together, which is something that we now do a lot of, correlating them together. So we have to make sure we've got the same loads, the same boundary constraints, and also we need to test to failure, because that's the only way ultimately that we're going to be able to correlate the life. And I'm going to talk about how we can do that in this session. So how has this impacted automotive design and aerospace by implication to the same thing? A friend of mine who is a tech specialist in an automotive OEM put it this way: we have 3 groups of people who are interested in fatigue. We have design engineers who simulate their designs and make them not fail. We have test engineers who try to make them fail. And then we have our customer. And if we're unlucky, they ultimately manage to succeed in that failure. So the vision is to characterize the customers, to then build a statistically representative test of that customer, and then to simulate the test. So how does this manifest itself in an automotive OEM, for example? Well, historically, we've probably gone to standards or past practice. So if it's a military vehicle, it could be Milstan 810, for example, or a military aircraft. Of course, if it's something like a car, you may be using an SAE standard in that, or your own in-house standard. But with novel items, it becomes necessary to actually go out and measure how people are using them. And that's what we're doing a lot more of today with electric vehicles. How do people really drive these around the world as we're designing a world vehicle now? Once we've done that, we can start to build a proving ground schedule. So we characterize the 95th% worst driver, for example, and then we'd be able to drive vehicles around a proving ground, and then we can measure loads. We can measure a lot more loads on a proving ground than we ever can on our highway. So in this way, we take our characteristic driver and we build a proving ground where we can measure the loads, and then we can start to build an accelerated qualification test for individual components. We can't sign off the whole vehicle on a proving ground because it has different accelerated damage rates for different types of component. So it's much better to do that in a laboratory. And then finally, we come to simulate that qualification test using computer simulation. Now, if we do that right, we can use the test in order to verify the simulation. And I'm going to talk about this in a minute. How do we do a test which can then feed into the simulation and vice versa? How do the two play together? Once we've verified that simulation, we can use the simulation to extrapolate different loading conditions and things like that too. And ultimately, what we want to do is validate the reliability target using a properly verified simulation model. So in that last section, we looked at the traditional deterministic design and looked how stochastic design in the present and the future looks. And we reflected on how that looks in fatigue, from the old build it, test it, fix it days to bringing in simulation, verification and validation. And now what I want to look at is how those simulation and tests sit together. How do they help each other? So first of all, we have to appreciate that simulation can be valuable before we do the test, during the test, and after the test. So let's have a look at each. So simulation before the test. What sort of questions do we want to answer with this? Well, the first obvious one is, before I actually invest in an expensive test rig, is it likely to pass? So we're going to say, well, what's the expected safety margin? Could I optimize the design further? And most importantly, am I sufficiently confident that I should commit to this expensive prototyping right now? Maybe if I had another month, it would be better and in the end work out cheaper. Another question we can ask ourselves is, where will it fail? So where should I look for this failure? Is it going to be subtle and I'll need extra instrumentation to spot it? Or is it really obvious? Where's the failure? And also, do these failure modes correlate with my previous experience and what I expect? Because if they don't, we may encounter a new type of problem, or we may be missing something. And then finally, is it okay to use a simplified test? If it's a shaker table, it might be a uniaxial test, for example. How does that actually affect the fatigue of my component? Do I get the same fatigue failures? How does it affect the life? Should I add supplemental axes to these? In other words, if it's a shaker table, shake it in Y and Z as well. So how does the test simplification also affect what I'm expecting? Of course, the simulation also plays a part while we're testing as well. So typical things that we might want to look at here is, where's the best place to mount sensors? If I'm trying to find the mode shapes, I want to find the places of maximum displacement. So again, simulation can help us to find that. It can optimize the positioning of strain gauges, accelerometers, displacement transducers and thermocouples, so we get the best measurements from our test. Of course, when we collect those measurements, we can also use virtual gauges on our FE models in order to validate them. A virtual strain gauge, accelerometers or displacement transducers. Is our simulation giving us the same response as we're physically measuring? And finally, we can do parametric analysis too. We can get parameters, such as modal parameters, for instance, which we know are critical in the response and the fatigue of a component. So we can use operational displacement shapes to make sure the natural frequencies and the mode shapes look the same. We can use experimental modal analysis or operational modal analysis to calculate the damping ratios. And we can use modal assurance criterion to make sure that our stiffness and our mass and our damping matrices are right and we're getting the right correlation. So we're using the test not just as a simple sign-off test, but in a way that we can feed back and verify our simulation model. And then finally, after the test's finished, what happens if it failed? Well, in that unlucky occasion, we can actually simulate the failure mode. We can take our simulation and say, what is it we got wrong? Can we simulate this failure mode to find that out? I can pretty much tell you it's going to come down to a difference in the fixing between the simulation and the test rig, boundary constraints in there, and damping ratios. They're the three critical ones. But once we've fixed it, we can then play what-if games to fix that problem so that the next time we test an article, we're guaranteed it's going to pass. Another thing that you can say is, how confident am I? I might only do 1 or 2 tests. How confident am I in that? What's my warranty exposure? Should I test to failure or just stop at a given target? And how many tests do I do? So you think about this as, say for example, a shaker table sign-off test. It's a bit like kicking a ball over a wall. You kick the ball, and at a certain given time, there's no failure. In other words, the ball's over the wall. And then you usually stop the test, don't you? You've got no idea what happened afterwards. Did the ball carry on? Would it have failed 10 minutes after or 10 days after? We're not really sure about that. And also, what happens if I kick a number of balls at the wall? How many clear the wall and how many don't? Because those that don't clear the wall, they're going to be our warranty costs. So here we find that if we want to verify our simulation, it's important to carry the test over to failure down here. But we can actually be smart on this. The nice thing about simulation is we can actually turn the volume up. So if your component's got to this stage and it's passed, we don't know whether it's going to fail in 10 minutes or 10 days. So let's just crank up the volume a bit. And maybe it didn't fail within 24 hours. So crank up the volume again. But the important thing is to test it to failure. And simulation, we can simulate the volume cranking up. But it's important to get that failure because that's what we can use to then verify our simulation on fatigue live. So we can use simulation in conjunction with physical tests to help improve our confidence. We can also look to see how, through simulation, to find out how reliability changes with different platforms or different users. Let's say, for example, that 5 years into our product run, we've started to see early failures in some of the vehicles. The question here is, am I going to be alarmed by this, or is this something I would expect as the early people coming in with their 5% accepted failure rates? Because we know that one battery module is probably put on different platforms in different countries with different drivers, all with their own different usages. Am I just seeing the worst case driver here? The nice thing with simulation is we can go back to our initial target mission profile and start to say, in this country we've got this scenario. Do I expect that they're my worst drivers? And is this something I should expect, or is it something I should be worried about and looking to remedy? So again, simulation is really good at doing this, spotting your critical users and also looking if certain users you would expect failures to come in early. So we can use simulation tests together. It's not one being better than the other, it's that they're better combined. And that simulation can go before the test, during the test, and after the test. So we've now looked at stochastic design and how simulation can fit in with testing. What I want to look at now is why it's important that we start to simulate uncertainty. And we're going to look at the sources of uncertainty, how we model that mathematically, and we're going to finish with a case study as well. So first of all, why is it important that we should model simulation uncertainty? Well, we know if we take 2 components off the same production line on the same day, and we give them to 2 identical customers, we would not expect one to fail at the same time as the other. We know that fatigue starts off at a microstructural level, and at a microstructural level, no 2 components are identical. Neither are the usage, really. So we tend to expect a factor of 2 to 3 in real life, just under normal conditions. As designers, we also know that we could probably expect 3 to 5 for a normal component, and 5 to 10 is not unexpected. So with that amount of variability, how can we suddenly compare test results from simulation with physical tests. How can we do it when there's such a whacking big gap? That's what we're going to look at here. But before we do, it's important that we understand the two different types of uncertainty. They are epistemic or reducible uncertainties and aleatoric or irreducible uncertainties. So epistemic uncertainties can be reduced by better knowledge, better measurements, better modelling, better understanding of your customers, for instance. We can reduce the amount of uncertainty. But aleatoric uncertainties, they're irreducible. They can't be reduced by better knowledge. They could be things of natural phenomena like the scatter that we get in material fatigue curves, for instance. The only way to change that is to fundamentally change the material you're going to use. You can't improve on it. They're naturally occurring. Now, these are important because if we find that our design is largely governed by epistemic uncertainties, we know that we could invest more money and therefore understand those uncertainties and reduce them if we could measure them. It may be economic to do so, it may not, but at least we have the decision. If our design, on the other hand, is governed by aleatoric uncertainties, there's nothing we can do to improve that. It's as good as it's going to get. And that's really why it's so important to understand which ones are your key uncertainties affecting your design. So where do the uncertainties come from in fatigue? So for this, we're best going back to the 5-box trick, remember, and there's those 3 inputs, and in those 3 inputs, we end up with uncertainties. So let's look at the material first. Now, our material uncertainties is governed by our fatigue curve, SN, EN, fracture mechanics, and so on. And we know that we end up with scatter about that curve, and these are aleatoric uncertainties. They're a function of that particular material with its different flaws and everything else in it. We also know, though, that there are epistemic uncertainties due to measurement. But as fatigue engineers, we pay particular attention to make sure we have the best quality measurement devices that are most accurate, extensometers, load cells and controllers, to make sure our epistemic uncertainties are very small in comparison to the aleatoric. We want to capture those aleatoric. We don't want to confuse that by throwing in additional errors due to our measurement epistemic uncertainties. How about loads though? Now, these can be a mixture really of epistemic and aleatoric uncertainties, and it sort of depends where they come from. So let's say, for example, we're designing a wind turbine or an aircraft and the loads come from design codes. Now, you may say in this case, what's the point in doing a stochastic design when actually we've been given factored loads? However, the factors themselves are usually known. So we've got an idea what the safety margins are, and that will help us in understanding reliability. But also many codes, we've also got a lot of options that we can choose too. There may be different load case permutations that we consider, or a different mix, for example. How does that impact our design? It's still really useful information in a stochastic design. Of course, we may be measuring our loads, but in this case, where do the loads come from? Do they come from real customers on real roads? Do they come from simulated usage on proving grounds, for instance? Or are they from laboratory tests like dynamometer tests? So here, again, we've got a mixture of epistemic uncertainties. Have we really captured enough people to find out our target customer? Have we got the right value for that? And also, there are measurement uncertainties that we're getting as well. So a mixture of epistemic and aleatoric uncertainties. And finally, more and more today, we're actually simulating loads. So we've got our model of our car going over a proving ground, for example, and then we're going to run that through a kinematic simulation, multi-body simulation, to chase those loads to the point where they're going into our particular component. So the simulation is also adding an additional layer of uncertainty on there. And then finally, we've got the geometry. So where did we find this from? Have we actually measured it using real production line components? Or again, is it simulated? So if it's been simulated through FE, for example, does our CAD geometry actually match with what is being produced at the end of the production run? What about our uncertainty due to finite element meshing constraints and problems with that? What about the constraints on the model itself and the loading? And how about parameters, in particular things like, have we got the damping there or have we just guessed it? So there's the parameters that are also affecting our simulation. So Again, lots of uncertainty there. A lot of that is epistemic. If we knew more, we'd be able to reduce that uncertainty and be more accurate. So now we've looked at the sources of uncertainty, let's look at how we can model that uncertainty. So in order to model uncertainty, it's called uncertainty propagation. So we start off on the left with the uncertainties, whether they be measurement, manufacturing, or parameters uncertainties. We then have to propagate those uncertainties through our analysis until we can quantify them at the end. That's the result. Now, when we look at uncertainty propagation, if you look online, you'll find that there is a lot of research going on. I split them into two methods, really. There's analytical methods and there's numerical simulation methods. The analytical methods are, for every mathematical operation, there is a corresponding uncertainty operation as well. So analytical is all about taking those equations and working out what the corresponding uncertainty calculation is. And you'll see lots of work. It's very easy to do things like linear static and linear dynamic. There's a lot of research work going on to nonlinear dynamic type analysis in this. Now, analytical methods work really well if you're trying to do a measurement transducer and look about the uncertainties through that transducer. But for us, we're looking at numerical simulation through finite element, for example. So for us, we're better off going down this route. And here we'll start to come across terms like Monte Carlo simulation, design of experiments, response surface analysis, and reduced order modelling or surrogate models. So I'm going to talk about those in a minute. Once we've propagated the uncertainties, we now end up not just with an average life, but with an idea of the probability distribution and the variability of that life. Okay, there's a lot of other things we end up with too. First of all, we can start to investigate. Is our principal, our most significant uncertainty, is it epistemic or aleatoric? So remember, if it's epistemic, we could reduce that uncertainty by probably investing more money and time into it. We can decide whether that's worth it. Or if it's aleatoric, it means that it's irreducible. It's just down to nature. It's important that we know which one governs our design. And the other thing we can do is we can start to qualify simulation with physical testing, even with a fatigue test where we know that there's tons of variability. So how do these work? And again, I've broken these down into two mathematical routes, which we're going to talk about. The first one is design for reliability. Design for reliability is understanding the underlying shape of the probability of failure curve or the reliability curve. It's all about trying to understand where the 95th percentile, the heart of that is. It's about quantifying the warranty exposure. It's about managing our maintenance schedules. It's about doing cost versus risk versus benefit analyses. The other one is design for robustness. This is about understanding your worst case scenarios, your edge cases. What happens if my worst driver gets hold of my worst product? Who is the worst driver? And things like that. It's looking at those edge case scenarios that interact. And I call that design for robustness. And the reason I separate them is there's two mathematical routes in the design of experiments. So we'll come to that in a minute. So how do we take a traditional fatigue analysis in our 5-box trick and turn it into a stochastic analysis? So first of all, our 5-box trick is what we call a deterministic process. That means if you've got the same set of inputs, you will always get the same output. It's deterministic. The output is determined. With a stochastic one, then the inputs can change statistically, and therefore our outputs change as well. So the way we do this is we change our inputs. So instead of them being constant values, we give a mean with a probability distribution. And then finally, we wrap our deterministic process inside a Monte Carlo wrapper. So this wrapper runs that process over and over again. And every time it runs it, it uses a different set of inputs from their probability distribution. The result of that is now for each failure mode, we get a range of answers coming out, and then we can start to do statistical analysis to understand that uncertainty and that variability. So the first question is, what is a Monte Carlo simulation? So I thought I'd just put a slide together just to illustrate what we're doing here. So let's say I've got an input parameter and it changes with a Gaussian normal distribution. Now, all I have to do to make this work is, first of all, I need to get a range of inputs, and I just use a standard random number generator. It generates a random number between 0 and 1 a number of times. In order to then shape that to fit my normal distribution, what I can do is project these onto the cumulative distribution. So remember, the cumulative distribution here again goes from 0 to 1. So now when I've got my random numbers, I can project them along and then look down, and then this tells me, this now gives me 5 parameters in this case. I'm only showing it with 5 just for simplicity, but these now have a normal distribution. In reality, I'd probably use a lot more than 5 to do it, but you get the idea. And by changing my standard deviation and mean, then I can change the way this looks. So whatever distribution I'm using, whether it be a normal distribution, log normal, triangular, whatever it is, I can use the same approach to get my input variables for my Monte Carlo simulation. And it doesn't have to be a continuous distribution either. It can be a discrete distribution like this. Now, okay, I've got 5 conditions here and I've only got 5 for illustration. Actually, I'd need, if I've got 5 discrete conditions here, I would actually need to be showing much more than 5 random numbers. But you get the idea, don't you? We can start to generate those random numbers, we can project them along to the cumulative distribution, and that then gives us this probability curve. So we've looked at how we can take a deterministic process, put it in a Monte Carlo wrapper, and then run it through a Monte Carlo simulation. You're probably thinking that rerunning an FE model over and over again 1,000 times, that's going to be expensive, and it is. And that's where we can make savings by using what's called a reduced order model or a surrogate model. Now, the nice thing is, in fatigue, we've been using surrogate models ever since we started doing finite element-based fatigue. So we take our fatigue results from the FE, we find the critical areas, and then we can calculate participation factors in that. So a scaling function between load and response. So we can do linear superposition and things. We could also take that not just linear static, but steady state dynamic as well. And it works through most of our cases. The only time when that fails is when we get highly nonlinear cases that we can't easily linearize. In that case, we may have to run the full finite element over and over again, but that doesn't occur very often. So we can use our surrogate model to make this calculation really, really quick. Now, there's another thing that we can do too. We don't want to be running thousands of simulations if we can get away with a fewer ones. So there's a process called design of experiments. Now, design of experiments is there to try and optimize our calculation space, our space that we're looking at. And this is where I've split it into 2. If we're doing design for reliability, trying to understand the heart of the shape of the distribution, then Latin hypercube methods work best. And I'll talk about those in a minute. But if we're looking for design for robustness, trying to find the worst case edge cases, then we can use factorial methods or a response surface method as well. So let's have a look at those right now. So what is a Latin hypercube? So a Latin hypercube is basically the same approach as we get with a normal Monte Carlo, except this time we're trying to force it. We don't want it clumping. If we do 1,000 simulations, for example, they tend to clump together. So what Latin hypercubes do is effectively, it's a way of forcing them into the areas. So let's say I want 5 random numbers. So my zone of 0 to 1, I'm going to split into 5 equal bands. And in each band, I'm now going to choose 1 random number. Of course, if I was going to use 50, I'd split this into 50 equal bands. But in each one, I'd find 1 random number. We take each random number again, we project it, and what you're seeing is that we're now ensuring we get a nice distribution over our statistical space. They're not all clumped together, they're now governing all of them, but the distribution is still, in this case, a Gaussian random approach. Now you're also thinking, okay, that works for 1 degree of freedom for one single input, but realistically I've got multiple inputs. So this is where the Latin square comes in. So a Latin square is where we've now got two random variables, x and y here. And the idea of a Latin square is, again, we split it. In this case, I've just chosen 5 equal intervals between over the distribution. And all a Latin square says is I want to have a single point in each row and each column. So here, if I've broken x into 5 and y into 5, then I've got 5 points. And each column and each row is used just once. That's what we call a Latin square, because it's square and there's 2 inputs in that. Now there are additional refinements we can make too. Let's say this point and this point ended up being very close together. Well, that's not good, is it? We've now got 2 simulations, but actually they're going to give very similar results. So there's an optimization we can do called maximize distances. So when we do this, we try and maximize the distances between neighboring points to make sure that we're not effectively running the same test twice. Another thing we can do is, if you imagine, there may be a way that we can fit a preferential line through here. That's not good either, because that's creating a correlation which may not really exist in real life. So again, we can minimize the correlation of points to make sure they're scattered further apart. And again, another refinement is, let's say that x and y aren't completely independent, but they have a relationship, a partial relationship with each other. In that case, we can also impose correlation between those random sources as well. So that again is an additional refinement we want to make. Now that's okay. We've now gone from 1 single variable to 2 variables. But how do we go to 3 variables and more? So a Latin square is 2 variables. And actually, to see how that works, we can look at that as a table. So I've now got random variable x and random y. And I'm going to choose just 5 points in my Latin sampling. So 5 random points in each of these bins for x and in y. And all I do to make that a Latin square is I randomly associate a point in x with a point of y, such that I only ever use the same points once. So that way we can now get our 5 different samples in our Latin square. Now let's just add an extra dimension to that. This is now 3-dimensional space. I do exactly the same. So each of my random variables now, I can generate my points, but I only actually use one combination of points once. And that's how I can very quickly and easily generate these experiments. So that is Latin hypercube sampling. It gets the word hypercube because Latin square is 2 dimensions, a Latin cube would be 3. Anything beyond that is our hypercube that's coming in. Of course, that's good at understanding the heart of the distribution. But what about the extremities? So for this, we could use a factorial method, for example. So in this case, I've got 2 random values, x and y, and I may want to look, well, it could be a maximum when one's at a minimum and the other's a maximum, or one's at a maximum and the other's at a minimum, or they're both at maximum, or both at minimum. So depending on this, I've actually got, if we just look at the edge cases, I've got 2 to the n possible calculations. So if I move this up to 3 variables, x, y, and z, that comes 2 to the power 3, which gives me 8 permutations. Of course, you soon find out that actually you might want to add, well, what happens if they're in the middle? That could be worse. So in that case, I suddenly start adding additional ones. And the more we add, then this scales massively. And that's where you may come up with partial factorial. So full factorial covers all of the combinations. Partial factorial is a method where we can reduce them. Or we could go to an iterative process called response surface methods. So this is iterative. We start off, first of all, by picking a few combinations. We run them, and then we actually project a surface through those, and we use that projection to say, actually, we need to run another one up here, because I think that's where the new maxima is. We run that, and then we come back and we fit another surface, and we iterate in order to find out where are the maxima in this case. So in this case, what we've now done is we've looked at design for reliability, understanding the heart of the distribution, the 95th percentile users and things like that, using Latin hypercube. We want to look at the edge cases, the worst case combinations. We're going to use either a factorial approach or a response surface method. So that design of experiment has taken us from a few thousand samples into a few hundred. So it's eased our workload by probably an order of magnitude, but we can ease it even more. To take it from a few hundred to a few tens, we can use some a priori knowledge. We know that we're looking for a fatigue type failure, and we know that that fits a log normal or probably a Weibull distribution. So with that a priori assumption, we're now not trying to fit a completely random sort of a profile. We are fitting a discrete shape, and we only generally need 2 parameters to do that. So we take all of those different failure modes and all of them, and now we're trying to find parameter estimates for a log normal or Weibull method. Now, there are 2 ways that we can do that parameter estimation. There's rank regression methods or maximum likelihood or MLE methods. And the reason we need these is because each one has its own benefit depending on where you are. So rank regression methods. This is really like fitting line on probability paper. It's like going through the old Weibull paper that we all know and love. Now, this case, Weibull is shown as the failures of a few discrete points, and we're actually plotting the on here we're plotting the statistical ranking versus the life, whether that be in time or cycles or whatever. We can then draw a straight line through that, and we can also calculate the confidence bounds of that. We can add a small addition to this. So maybe we've got things like runouts. So the test reached the end of the test and we stopped the test, but we didn't see a failure. So it could have actually failed any time after. We can actually build that into this rank regression method too. But really, you're better testing to failure all the time. In that way, we now get some points nicely anchored here. So rank regression methods, they work very well when you've not got many tests. So physical tests tend to work well with rank regression methods because there's just not usually a lot of them. Maximum likelihood offers a lot more flexibility, but generally works when we have a lot more tests or simulated results, for example. Now, this adds a number of benefits. Not only can we look at a discrete test tested to failure when we measured the actual failure time here, but we can also look at these run-out tests too. So in this test here, we knew that when we looked at it at time x2, it was fine, and we just stopped the test. So if we hadn't have stopped the test, it would have carried on and failed at some point, but we're not sure when. So we've actually got this area under here that we need to find. And maybe we've got what we call an interval censored one. So here, on Tuesday night at time x3a, it was fine. But by the time we got in on Wednesday morning at time x3b, it had failed. So sometime between Tuesday night and Wednesday morning, there was a failure, but we're not sure when. So again, this gives us this band under here. And what we do with maximum likelihood is we actually try and maximize the area under that. We use this by what we call a log likelihood function. So we try and minimize that log likelihood function, and that then allows us to find our parameters in here. If it was a Weibull, it would be beta and eta. If it was, say, a log normal, we'd be looking at log mean and log standard deviation as those parameters. And by doing this, we can estimate those. And there are also methods here of estimating the confidence bounds for those too. A few tips if you're doing finite element. If your simulation in one of your runs says beyond cutoff, because it just happened that in that combination you were below the endurance limit, for example, then we can take those into account. We can call those a suspended test. And when we do that, we set the life limit to our cutoff limit, our endurance limit, and that works really well in our stochastic simulation. Of course, you may also find that a couple of results come back as static failure. You may have exceeded UTS, for example. Now, in this case, it's much better to then go and do a robustness analysis to find out, so why did that possibly occur? Is that an outlier case that we're looking at here? Or if it isn't, maybe I've got a design problem with this and it's just not fit for purpose. So static failures, we can start to investigate by a robustness analysis and say, is this really a viable concern that we get this extreme combination? Or is it something I do expect in common, in which case it might be indicating that I've got a design problem. Of course, when we analyse this, that just gives us one or two failure modes, or one component, the fatigue of one component. But we know that component is then added with other components to make the combined system. How do we ensure the reliability of the entire battery pack, for instance? And this is where we can use system of system simulation. So using those probability of failures, those reliability curves that we've just got, we can then build those into a system of system simulation. So, for example, we can simulate then serial systems. So in a serial system, a failure of any particular one failure mode will cause the death of the entire battery pack in our case. A parallel system actually means we've got redundancy. So in order for the pack to fail, we need death of 1, 2 and 3. And of course we can combine them, we can have reduced performance if one fails, and all sorts of things like this. But the nice thing is we can analyse that in post-process really quickly, and we can start to do lots of analysis on our complex system. We can start to do quantifiable risk exposure. What is the risk of my battery failing prematurely and incurring a high reliability problem? How, by making changes, does my reliability grow? Can I improve the reliability? How do I design my maintenance to ensure I've got preventative maintenance coming in at the best possible time to be both reduce my risk but also reduce my cost as well? So there's all sorts of analysis we can do once we've got this stochastic result. So we've looked at the sources of uncertainty, how we model them mathematically. Let's finish off with a case study. So in this particular case, we're looking at the fatigue of an air-cooled intercooler. And we can see highlighted here is where the failures are occurring. And in this test, it's actually performed at a high temperature, so the intercooler is kept at a high temperature, and then we provide pressure cycles. And we can see they've done 5 physical tests here. The lowest life was 350,000 cycles to failure. The highest one was 650,000. So the average life is about 500,000 cycles, and there's about a ratio of 2 between the highest and the lowest. And we've also done finite element analysis to find the hotspot and to calculate the life based on that. But in this particular case, we just want to look at 2 different types of uncertainty. We're first of all interested in our material scatter, which, as we've learned before, is an aleatoric uncertainty. It's irreducible. It's a function of the material we've chosen to use. We're going to have to change the material if we want to change that. So this is irreducible. We're also looking at FEA modelling errors. These are epistemic. So in our case, we want to see, is there a benefit in improving our model? So we've got a crimped component here. We've not taken into account any residual stresses though. We've not taken into account the contact elements. We've not taken into account the fact that we've got a composite tank which has a different expansion and everything. None of that we've taken into account. Does it pay us to do it? Do we need to invest in better FEA modelling? Or, in this case, would the material scatter account for most of it? So the first thing we can do is to compare our simulation that we have today with our tests. So even though there's a factor of 2 on the tests, we can still fit our probabilistic model. So the black points here are our 5 physical tests, and we can do our Weibull analysis here. And the dotted black lines, that's our 90% confidence bands. Now, if we superimpose all of our simulated curves, we find that for most parts, they fit really nicely in this band. They start to pop out a little bit above here. So in the high cycle end, maybe our simulation isn't as good, but for most of it, it works tremendously well. Now, as well as that, we can look at the contour plots. So what's a contour plot? So we know that a Weibull analysis has 2 parameters, beta and in this case theta. Now, with a 90% confidence, our tests, beta and theta, lie somewhere within this contour here. And again, at a 90% confidence, our full simulation is in the red. And the fact that the black and the red curves overlap is telling us that we can accept this simulation at the 90% confidence level. But more than that, if we look, we can start to see how does material variability and FEA variability compare. So here, the material variability is very broad, yet the finite element variability is very narrow. So what this is telling us is that most of this variability we're looking at is due to material variability. That's an aleatoric uncertainty. We can't do anything about it. Sure, we could invest more in FE, but even if we made this narrower, it wouldn't change our design. So our current approach to FE is good. And of course, from this, by combining the tests and combining the simulation, we're much more able, with a high confidence, to say, I'm happy with this target, I'm happy with my reliability estimate, that my simulation is actually starting to be verified by my test. So what has this shown us? It's shown us first that simulation gives excellent correlation with experimental results in this case. The model offers a reliable platform so we can perform additional design simulations if we want to, and can extrapolate and create reliability statistics. And it's also shown us there would be no economic advantage improving the FEA simulation. The precision in this case is limited by the material behaviour, not our finite element simulation. So we've reached the end now. Let's have a look at where we are. So at the beginning, we started to look at what is stochastic design, and it's all about trying to understand and model uncertainty. We looked at how, in fatigue terms, we can take the build it, test it, fix it, which was test-based, and bring in simulation. And we saw how simulation and test don't compete with each other, they work hand in hand to support one another. We then looked at how we actually can quantify uncertainty. How do we model it? Where does the uncertainty come from? How do we mathematically model it? And we looked at a case study. And now, in conclusion, we can actually see that there are significant benefits in going for a stochastic or probabilistic fatigue design over deterministic, because it's all about simulating uncertainty, and there's tons of it when we deal with fatigue. Yes, we get the average life, but we also know the variability in life for each of the failure modes. It means we can start to identify the most critical inputs. So of all of the variability, which ones are affecting my design most? We can use that to optimize our design for uncertainty. That means we can avoid large safety factors, and we can minimize our risk exposure. And we can also find out whether these are aleatoric or epistemic uncertainties. We've looked at design for reliability and design for robustness. So design for reliability, remember, the Latin hypersquare and things, is all about finding the heart, the shape of the distribution, and the 95th percentile. So in this case, we can design for an acceptable reliability target. We can quantify our warranty exposure risk. We can manage maintenance schedules. We can do the cost versus risk versus benefit analysis. And this enables us to ensure we've got a good brand image and reputation. Of course, design for robustness is all about understanding the edge cases, the worst case scenarios, to make sure that the worst driver doesn't get hold of our worst production model and things like that. We can also validate, most importantly, simulation with physical tests, even accounting for that huge amounts of uncertainty associated with fatigue. And this means that we now start to get verification and evidence that we can now trust our simulation. And finally, we can bring in all of those separate failure modes, and we can take those probability distributions to use system simulations to take them from tiny components to subcomponents to entire systems in order to see how they impact on our reliability warranty. So I hope you've enjoyed that presentation, and if you have, and you want to read more, then there is a paper available and we can send that paper to you. So please get in touch with us. I hope you've enjoyed it. Thanks then. Bye.